Okay, so just looking at this cross product a little bit more here, what is this sine of the angle? It's the sine of the angle span between the two vectors. So you have your QV vector and your B vector. I showed you how to set that up with your hand the other day, but let me remind you how it connects to torque. So you can remember that torque was R cross F. And so if you had something being torqued, you'd have an R vector, and at the end of it you would draw an F vector, and you would decide, oh, this rotates in a way that is counterclockwise. And then what does counterclockwise mean? That means positive, right, Z direction, which is out of the page. So same thing here. If you look at this second picture, figure B, and take that B vector and put it on the end of your V vector, right, then you would see that this rotation in a torque would cause a rotation that is like this, counterclockwise, right? CCW, making a positive torque. And you notice that's not a perfect cross product. That's not a theta of 90. So you can take in what's torque perspective, like the lever arm idea, right? Where you're really thinking about, oh, just the Vx. Here is a perfect cross product. So you see this is sine 90. And again, that creates the torque that's around. So that's how you can relate this thought and this right-hand rule over to torque that we were doing before, just to connect the way you cross-product quantities together. Okay, let's practice using the expression mathematically, QvB. Okay, so here you have a view of a motion where a particle is moving and it experiences an inward force. This velocity is only in the xy plane, right? And that makes force kind of in the radial direction, in towards the radius. But here's an example of a particle that not only has that motion in the xy plane, but also has some motion that is parallel to the B. And since that motion doesn't get affected by the magnetic force, because F is QV cross B, right? There is a certain part of velocity that does not get changed. And so that kind of creates this helix pattern that we see over here on the right. Good. So again, what you can do mathematically is you can set F equals QVB sine theta using magnitudes, and you can set that equal to mv squared over r, or you could have just said mac, that's fine too, right? Whatever. And from here, what you can do is you can simplify to find an expression for radius or b or what have you. So if our sine theta is perfect, then we can call that 1. We can cancel our v's on one side and we can solve for the radius that this particle would make. So r would be mv over qb. After viewing this concept in class, we'd look at my Helmholtz coils in the back. They're a big set of two like red coils. They run current through them, and this glass globe in the middle filled with gas. And what we do is we turn up the accelerating voltage. And what does that do? That spits a beam of electrons out of our cathode ray tube.
And you can see the green or blue beam coming out of that cathode ray in that direction. And there's no magnetic field here, so this is just going straight out. And we can measure the energy of that by how much voltage we're giving it.
And then what we do is we turn on the current in the coils. So we take this, and our current begins to flow through our coils. Some current in our wires, let's say like this. Now, we know by using our right hand from the very beginning that we can find the direction of the magnetic field through this setup. So when we do that, take your right hand, take your fingers, follow I, and you find that there's a B that travels through this region, right? B, there you go, coming out of this. So now you know that this beam of electrons, right? These are electrons, and Q, electron charge with the velocity. We now know that when they experience a magnetic field, they're going to experience a force due to that magnetic field. F is QVB, right? Across B. So this is a quantity that is left, because remember, we're dealing with electrons, and this is out. So go ahead and take a minute and find the direction of force. Line up your hand, and you'll find the force is up. So then our beam of electrons is going to begin to bend up, when we turn on the current, like this.
I'll show you. Cool. So just going to bend it around, close up, zoomy zoom. If I have a larger current, the cathode ray beam will turn all the way around into a circle, essentially. If I have less current, up to 0, it goes straight.
Our beam will go all the way around in a circle if we make the B strong enough. And inside, there's a little measurement device where we can actually get the radius of this curvature. And between the information of the accelerating voltage in the cathode ray tube and the current in the coils and the radius of the curvature, you can actually do calculations for the J.J. Thomson experiment and calculate the charge to mass ratio for an electron. So here are some examples. Problems, I just tried to make them a little creative for you. I want to warn you about your units, right? Don't use centimeters. Remember, our magnetic field is measured in Tesla. Our first question wants you to connect in the magnitude of linear momentum, P. Remember, P can be written as mv, so when you see mv in your equation, you should sub it out for P. Now, what is the magnitude of angular momentum? So when you see rmv, the answers are here, and I'll put the work up online.